Every time you drive your car, watch the rain fall, or even just walk across the room, you're in a constant dance with these powerful, invisible forces. Today, we're going to pull back the curtain on three of the big ones: friction, drag, and the force that makes things turn. And we'll start with a little puzzle that really brings them to life.
Okay, I know it sounds like the setup for a really weird joke, but it's a serious question in the world of physics. You've got a record-breaking skid mark, a cat that survives a fall from a high-rise building, and a daredevil cyclist who literally defies gravity. The answer? The thing that connects all three lies in understanding the fundamental forces we're about to dive into.
All right, first up is the force that both stops us dead in our tracks and, weirdly enough, allows us to move in the first place. I'm talking about friction. It's totally unavoidable and, honestly, it's essential. Without it, you couldn't even hold a pencil, let alone walk down the street.
Let's start with a really simple observation. You give a book a good shove across the table, and it slides, then it stops. Ever really think about why? According to Newton's laws, if its velocity is changing, and slowing down is a change, there absolutely must be a force causing that change. That invisible force, the one that's always pushing back against the direction of motion, well, that's friction. Now, friction is clever. It behaves in two completely different ways depending on whether something's moving or not. So imagine you're trying to push a heavy box. As you can see in step 1, you push just a little bit, and this invisible static friction pushes back with the exact same force. The box doesn't budge. Okay, step 2, you push harder. Static friction just dials up its resistance, still matching you perfectly, but it has a limit. That brings us to step 3, the breakaway. Your push finally overpowers that maximum static friction, and the box lurches forward. And here's the really crucial part in step 4. The second it starts sliding, a totally different, weaker friction called kinetic friction takes over. And you can feel it, right? You don't have to push quite as hard to keep it sliding.
So what in the world is going on at a microscopic level to cause all this? Well, surfaces that look perfectly smooth to us are actually, on a tiny scale, incredibly jagged. Think mountain ranges. When you put two surfaces together, only the very highest peaks actually touch. The pressure at these tiny points is so immense that it literally welds them together. This is called cold welding, and it's the real source of static friction. To get that box moving, you have to apply enough force to break thousands of these microscopic welds all at once.
Okay, let's put some physics to this. On the left, you've got static friction. Like we said, it's variable. It always matches your push, right up to a certain maximum. That max value is determined by two things you see in the formula. First, this Greek letter μs, which is the coefficient of static friction. You can just think of it as a grippiness score between the two surfaces. The second is Fn, the normal force, which is basically how hard the surfaces are being pressed together. The heavier the object, the bigger the normal force, and the more friction you get. Now, on the right, we've got kinetic friction, which is for objects already in motion. Its formula looks similar, but its value is constant, and it's determined by its own coefficient, μk. And here's the kicker. μk is almost always smaller than the static one. And that, right there, is why it's always easier to keep something moving than it is to get it started in the first place. So the really cool part is that we can use these principles to solve real-world mysteries. Get this. In 1960, a Jaguar skidded to a stop on a highway in England, and it left an unbelievable 290-meter trail of rubber on the road. That's nearly the length of 3 football fields. This is a textbook case of kinetic friction at work, and with a little bit of physics, we can act like forensic investigators and figure out exactly how fast that car must have been going.
So here's how the investigators would have cracked the case. As you see in step 1, it all starts with Newton's second law, force equals mass times acceleration. The only horizontal force slowing that car down is kinetic friction, Fk. Then, in step 2, we just substitute in our formula for kinetic friction. Now we can figure out the car's deceleration A, and here's a really neat part. You see how the mass m cancels out? It literally doesn't matter if it was a tiny sports car or a huge truck. Finally, in step 3, we just plug that deceleration into a standard equation of motion, and we can work backwards from the skid distance to find the car's initial speed.
And the result? An absolutely mind-boggling 210 kilometers per hour. And get this, that's a minimum estimate, because the car was actually still moving when it left the road at the end of the skid. It's just a perfect example of how understanding a force like friction allows us to reconstruct the past from the clues it leaves behind.
Now, this whole idea of a resistive force doesn't just apply to solid objects grinding against each other. Oh no. It also happens anytime an object tries to plow its way through a fluid. And by fluid, I mean something like water, or even just the air all around us. This brings us to our second big force, drag.
So the force of drag depends on a few key things, and they're all right here in this formula. You've got c, the drag coefficient, which is all about the object's shape. Is it streamlined like a bullet, or is it blunt like a brick? Then there's the Greek letter rho, which stands for the density of the fluid it's moving through. A is the object's cross-sectional area, how big of a target it presents to the fluid. But the most important factor, by far, is speed, v. And notice how it's squared in the equation. This is absolutely critical. It means that if you double your speed, the drag force doesn't just double, it quadruples. This is exactly why it gets so much harder to pedal your bike faster and faster against the wind.
And this is a brilliant illustration of how athletes use that drag equation to win. Downhill skiers get into this tight egg position for one simple reason: to make the A, their cross-sectional area, as tiny as humanly possible. By minimizing their profile against the wind, they slash the air drag and can reach some absolutely blistering speeds.
That powerful v-squared term leads to a really fascinating phenomenon for any falling object, a kind of ultimate speed limit. See, as an object falls, it speeds up, and as its speed increases, the upward force of air drag increases dramatically. Eventually, that drag force grows so large that it perfectly balances the constant downward pull of gravity. At that point, the net force becomes zero, the object stops accelerating, and it just continues to fall at its maximum possible speed. We call this terminal speed.
Let's visualize how this tug-of-war plays out. So, when an object first starts to fall, its speed is close to zero, so drag is basically nothing. It's just accelerating down because of gravity. But as its speed builds up, that upward push of drag force grows and grows, fighting back harder and harder. Finally, it reaches that critical point where the upward push of the air exactly equals the downward pull of gravity. The forces are perfectly balanced, acceleration slams to a halt, and the object has officially hit its terminal speed.
And that speed limit is totally different depending on the object's shape and weight. A typical skydiver might top out around 60 meters per second. A denser, more aerodynamic baseball only gets to about 42. A large raindrop hits its terminal speed at just 7 meters per second, which is great news for us because it's why rain doesn't hurt. And a parachutist, by using a canopy with a huge area to maximize drag, can slow all the way down to a gentle 5 meters per second. Skydivers are just absolute masters of manipulating drag in real time. By changing their body position from a head-down dive to a spread eagle, they can dramatically change their cross-sectional area, A, and in doing so change their terminal speed. This lets them slow down, speed up, and fly relative to each other. And sometimes, this deep intuitive grasp of physics can be the difference between life and death. This is the incredible true story of Gregory Robertson. During a group jump, he saw a fellow skydiver, Debbie Williams, get knocked unconscious in a mid-air collision. To save her, he had to perform an absolute masterclass in applied drag physics. First, he went into a tight head-down dive, minimizing his area to boost his terminal speed to over 320 kilometers per hour, just so he could catch up to her falling body. The moment he reached her, he instantly shifted into a widespread eagle, maximizing his drag to slam on the air brakes and match her speed. He was then able to deploy her parachute just 10 seconds before she would have hit the ground. It was an absolutely heroic rescue, and it was only possible because of a complete mastery of physics. So, we've looked at forces like friction and drag that basically resist motion. But what about the force that changes an object's direction? See, any object that's moving wants to keep moving in a straight line. To make it deviate from that path, to force it into a curve, you need to apply a very specific kind of force.
We call this centripetal force. And probably the most crucial thing to understand is that this isn't some new, fundamental force of nature. Centripetal is really just a job description. It means center-seeking. It's the net force you need to pull an object into a circular path. That job can be done by the tension in a rope, by gravity, or by friction. Now look at the formula. The force you need gets bigger with more mass m or more speed v. But pay special attention to the radius r on the bottom. Because it's in the denominator, a tighter term, one with a smaller radius, makes the required force just skyrocket.
So why does this force feel so different in different situations? Well, think about being in a car that's taking a sharp turn. The centripetal force that's holding you in that turn is the car door pushing on your side. It's a contact force, acting on one side of your body, so you feel it. You feel compressed. Now contrast that with an astronaut in the space shuttle. The centripetal force keeping them in orbit around the Earth is gravity. But here's the thing. Gravity pulls on every single atom in their body, all at the same time and all equally. Because there's no single point of compression, they don't feel any force at all. And that's the very sensation we call weightlessness.
And speaking of thrilling applications, check out this incredible stunt from way back in 1901. A performer who went by the name Allo Daredevil Diavolo would ride his bicycle in a full 360-degree loop-the-loop. Pulling this off without falling from the very top of the track required an absolutely perfect intuitive understanding of centripetal force.
Okay, so picture it. At the very top of that loop, Diablo is completely upside down. You've got two forces pulling him down, toward the center of the circle, the force of gravity and the normal force from the track pushing down on his wheels. Together, those two forces have to provide the exact amount of centripetal force his speed requires. If he goes too slow, the centripetal force needed is less than the pull of gravity, and he'll simply peel off the track and fall. Physics tells us that the absolute bare minimum speed he needed at the top to stay glued to that track was 5.1 meters per second. Any slower, and the stunt ends in disaster.
And this exact same principle is what keeps us safe on the road every single day. Ever noticed how highway off-ramps are banked or tilted inward? On a flat curve, the centripetal force making your car turn comes entirely from the friction between your tires and the road. But by banking the curve, engineers cleverly tilt the normal force, that upward push of the road. A component of that tilted force now points toward the center of the turn, and it helps friction do its job. This means you're less reliant on pure grip, which makes the turn far, far safer, especially if it's wet or icy.
So, there you have it. From the microscopic welds that keep a box from moving, to the air resistance that sets a speed limit on a skydiver, to the center-seeking force that keeps a daredevil on a looping track, our world is shaped and governed by these unseen forces. They really are the invisible architects of motion. The question now is, with their secrets revealed, where are you going to see these forces at work next?